So last time we did some work to look at a composition of function. So if I'm integrating a composition, I want to pick the inside function to be my u, and then I hope I have a du where I can cancel it nicely to get only an interval of u, only an integral of u. And then I can integrate a power of u, or sine of u, or cosine of u, or e to the u, things like that, by knowing the antiderivative. So we had full control over u, but you're stuck with du once you pick u. We looked at a couple examples when du was dx. In the case du and dx, u is known as something called a dummy variable because you're just simplifying sine of something, and if the derivative of that something is 1, you could just say, okay, I'm just going to say that's sine of u, because I know the integral of sine of u is cosine of u. And then I plug in what u is in terms of x. We looked at an example, though, in the same setup, except that our du was not dx by itself. It had a constant to deal with. So we talked about two methods to do that. I could solve for dx in terms of du, plug it in to see what cancels or what the constant, how to deal with the constant, or I can manipulate the original integral to be exactly what I want by multiplying and dividing by a constant that is convenient. So here, our answers look very similar, but this one's off by, this answer is multiplied by a 1/6 because the derivative of our u was 6. And then we did an example, kind of the same setup. Here, the u was x minus 8, so du is dx, so we don't have to worry about a constant being manipulated there. But the example when our du was 2, we have to divide through by 2 because our du is 2 dx, so we need a 2 dx to cancel. So if I have a 2 on there, I need to divide by 2 to make it equivalent. We looked at sine of x times cosine of x. I let u equal sine of x. Du is locked in to be cosine of x dx. Simplifying the integral, I get a term. I get the integrand is only a function of u. Integrate it straightforward, and then back substitute. You can always check yourself by taking the derivative to confirm that is correct. We looked at a little bit more complicated examples with tangent inverse, and there will be some on Wiley that will give you the form and have you pick what a is and what u is, and then you plug that in. So it's pretty straightforward once you know the overall form, how it's being manipulated. Today, we're going to finish this section, and then we're going to talk about a little bit about 5.5, mostly just kind of introduce it to you. There won't be any homework on 5.5 on Wiley or written, or on the final exam or this fourth exam. 5.4, sorry, 5.4 won't be covered. But I'm going to kind of introduce it to you. It comes up a little bit in Calc 2, and so just some exposure to it, but I'm not going to have you do any problems on it. And then we'll go over the beginning of 5.5. So this is 5.3, day 2. So I'm going to scan this in. This will be the new page 1. So I want to start off with some less apparent substitutions. So the integral of x squared times the square root of x minus 1 dx. I have two choices for my u. What would you pick to be u? X minus 1, so if I let u equal x minus 1, then du is dx. We like when du is dx because we can just plug that in. But if I do, I would have x squared, the square root of u, du. Can I write x squared in terms of u? I can if I'm creative. So do you see what I have here? Could I solve for x and then square it? So what's u equals x minus 1? What would x equal? U plus 1. Well, if I know x is u plus 1, then what is x squared? Right? So I was able to write x in terms of u, and I was able to write x squared in terms of u. And I could write x cubed in terms of u. I could write x to the 57th in terms of u. It would not be fun, though. But you can do it. So here or here? Here, yes, from my u. I can let this be. I have no problem saying, you give me a number, x, and I will transform that number to u. So if you give me 5, I say 4. If you give me 3, I say 2. If you give me 57, I say 56. But that's not going to change the function. It's not going to change where I evaluate the function. I'm just saying everything I'm inputting, I'm then subtracting 1 to that and inputting u. So that just makes it easier to integrate something in u, and then I'll reshift it after I integrate it and say, okay, well, u is really x minus 1. So now I can write x squared. X squared in terms of u is u squared plus 2u plus 1 times the square root of u du. At this point, the best approach is to get u to a power. So I need a FOIL. What is u squared times the square root of u?
U?
No.
U
Over 5, u to the 5 halves, right? When you have like bases, you add exponents. So 2 plus a half would be 5 over 2. What's u times u squared? 1 plus a half, 3 over 2, plus u to the 1/2 du. It's convenient to write u as a power of u to a power, so the square root of u, you would write u to the 1/2. So if I had a, the square root of x to the b, I would write that as x to the b over a, right? So that might come out, if I have, you know, the 6th root of x, I'd write that as x to the 1/6, because I can integrate that straightforward by the power rule that we talked about. So now I have u to a power. I have all my u's to a power, so I can integrate that. So what is the integral of u to the 5 over 2? U to the 7 over 2 divided by 7 over 2. Plus 2u to the 5 over 2 divided by 5 over 2. Plus u to the 3 over 2 divided by 3 over 2 plus c. So cleaning this up and back substituting what u is in terms of x, I have 2 x minus 1 to the 7 over 2 divided by 7 plus 4 x minus 1 to the 5 over 2 divided by 5 plus 2 x minus 1 to the 3 over 2 divided by 3 plus c. And that's your answer. If you differentiate this and add like terms, you get back this. That's all.
It's pretty straightforward.
If you need to find the derivative of that on the test, that would probably just not.
Are you kidding me? The derivative. What is the derivative of this first term?
X minus 1. No.
X minus 1 to the 5 halves. This term, pretty straightforward again. And this, because the derivative of the inside is 1, so it's
I would
not...
just look at it and be like,
I know, but it's not that dramatic. Come on, guys. It's, you know.
you're not going to put that on there.
She's totally gonna put
You guys are... So, yeah, sometimes you just got to take a breath and say, okay. You know, this next test is all pretty much integration, right? There will be 4.8, which has to do with differentiation, with the mean value theorem and Rolle's theorem. But all chapter 5 and 6 is all integration. So I might ask you to integrate something like this, but then once you get here, I won't necessarily ask you to differentiate it to show it's the same. This is the less apparent one. You actually don't have any of these on Wiley that are like this. The ones that are on Wiley are very, very straightforward. Like this one, we did one like this in class. We're picking u to be 8x minus 7. So then du would be 8 dx. So I have a 1/8 in there. Question?
Okay, so the point of u substitution, you don't want to get like an x and a u in the same term.
Correct.
Right.
In the
So
same
that's like this.
integral.
That's the only.
Well, the point of the u substitution is saying, I know how to integrate u to the
Yeah.
9th power. Here. But I don't necessarily know 8x minus 7 to the 9th power.
Have those rules.
Yeah, we don't have that general form. So I can transform it into a simpler integral, integrate that, then back transform it to the original function.
I think I kind of forgot you said your du has to match something.
You always have to find du and replace it in terms of x. So if we go back here, I have the integral dx. So my function should be a function of x. Here I have the integral du. I have a problem because my x squared did not cancel. So I need to manipulate that to be in terms of only u. As soon as I do that, I'm good.
So that's what you mean by having your du match.
Yes. Your du,
Only in terms of u.
your integral only has to be in terms of u. If you have an x here, your integral can only be in terms of x.
How did you decide what to turn your x squared into?
I have no control over what x squared is. I let this u substitution be x minus 1. So if I solve for x and square it, I get x squared. But I don't decide that. I can only pick u. After that, everything is locked into algebra.
Did you square it as
Because I needed to replace this x squared.
if it was just
If it was just x, I would replace it with u minus 1. Then I would distribute the square root of x to u plus 1. Thank you. If it was just x, I would replace it with u plus 1. If it was x cubed, I would replace it with x cubed plus 3x squared times 1. Yeah, because I could use 1, 2, 1, 1, 3, 3, 1. So x cubed, 3x squared plus 3x plus 1. And then FOIL it too. Question?
So how do you know they want to choose they want to use as your u variable?
You practice. Yeah, if I would have picked u to be x squared, the derivative of x squared is 2x. I don't have a 2x to cancel, so I can't do that. A lot of times you'll pick the u that the derivative is also simpler. So here, I want to pick what's under the square root because I can't necessarily take the square root of, I can't square root both sides, but I can square both sides. Yeah, so let's look at some that are on Wiley. This one's straightforward. This one is semi-straightforward, except for the fact that if you pick your u, your du cancels everything and you're left with 1. But the integral of 1 is u, right? So let's write this one out. This is 5.3, number 19. So we're integrating secant of 5x times tangent of 5x dx. What's the derivative of secant? Secant tangent. What's the derivative of tangent? Secant squared. I don't have a secant squared to cancel, so I need to pick my u to be secant. So I'm going to say u is secant of 5x. So what is du?
Secant, second.
Secant of 5x times tangent of 5x times 5 times dx. Right? So if you notice, I don't have a, if I plug in u, I don't have a secant tangent to cancel. So I'm going to manipulate this. I'm going to solve for dx. dx is du divided by 5 times secant of 5x times tangent of 5x. So if I plug in what dx is in terms of du, I get the integral of 1 du over 5. Sorry, 1 over 5 du. So you can kind of see that if I have the integral of secant of 5x times tangent of 5x times dx in terms of du, tangent of 5x cancels, secant of 5x cancels, and I'm left with 1/5 du. What is the integral of 1/5 with respect to u? The derivative would be 0. Amanda?
Did you pull out the 1/5 from the dx equation?
From here,
From down dx equation?
Dx is du over.
here.
Yeah.
So I solve for dx. So dx would be du on top divided by all this.
I get that.
So I have du divided by 5 times secant of x times tangent of x. So if I plug dx into my integral, I'm left with 1/5. This is dx.
Oh, so all you did was plug in dx?
I plugged what dx was in terms of u. Question?
I don't understand how you get du. Like, how did you find that?
You know how we picked u, right?
Right.
So du is just differentiating u. What's the derivative of u? That's du. What's the derivative of secant of 5x? Secant of 5x times tangent of 5x times 5 with respect to x.
Okay.
Question?
So since du cancels the secant 5x, tangent 5x, you don't have to substitute.
There's nothing left to be u.
Okay.
Yeah. So in this case, it all canceled except for 1. If I would have had an extra, if this was secant squared, then I would have a u here. If this was secant to the 80th power, I would have secant to the 79th power here. So that would be u to the 79th.
So the answer was 150?
The integral of 150u is the integration.
How did you get 150u?
So from here, I said, okay, I need a secant tangent dx to cancel to get it in terms of u. So I solve for dx in terms of du, replace that, and I'm left with a 1/5 du. The secant cancels with the secant here, the tangent cancels with the tangent here, and I'm left with 1 over 5 du. So now, what is the integral of 1 over 5
X on
with respect to u? U over 5, or 1/5 u, right? So 1/5 secant of 5x plus c.
Yeah, just substitute the answer.
Because u is secant of 5x. Question.
Could we have done 5x for u instead and then just
You-
done direct conversion over to...
You would have to do, yeah, you could do that and say, you know the integral of secant of u times tangent of u, because the derivative of secant is secant tangent. Right? If I differentiate this, what do I get? Secant of 5x times tangent of 5x, right? Because times 5, but I have 1/5 here, so the 5's cancel. So you could say, okay, you don't necessarily have to show the u substitution here. This is why it works. But you know that the derivative with respect to x of secant of x is secant tangent. Or tangent secant, same thing, right? So if I integrate tangent secant, I get secant. So I could do a u substitution here to be 5x. I could say with respect to x, I could say let u equal 5x, then du is 5 dx, so then I have the integral of 1/5 secant of u tangent of u du, which I know the integral of secant of u tangent of u is just secant of u. So this is 1/5 secant of u plus c, which would be 1/5 secant of 5x plus c.
How did you pull out the 1/5 if you substitute?
I solve for dx. dx is du over 5. So everywhere I have a dx, I plug that in, and I have du over 5. So that du over 5 is 1/5 times du. So I can pull that 1/5 out. From the theorem in 5.2 that the integral of a constant times a function is a constant times the integral of the function.
So you're just doing the same thing like we did with our related rates, where you're substituting in du over 5 for dx, right?
Yeah.
So instead of seeing dx, you're using du over 5.
Yeah, because I want to get my integral in terms of only u. So I have to replace dx with what it is related to du. These are related rates, kind of like that. You can say that u is a function of x. So if I differentiate u, I have to differentiate this function of x. So I have 5 dx.
So can we do it in either way?
Yeah, you can do it either way. So let's look at another example where we have some things
Get
that...
rid of it. You went from 1/5 du to just 1/5 u.
Here?
Yeah.
Yeah, I integrate 1/5. What's the integral of 1 with respect to u? U. What's the integral of 5 with respect to x? 5x. The integral of a fifth with respect to x would be 1/5 x. The integral of a constant with respect to x is that constant times x. The integral of 5x with respect to x would be 5x squared over 2, right? The integral of a constant with respect to x is a constant times x plus c. So the integral of 5 with respect to x would be 5x plus c.
You can also think of it as like x, all these things.
You can, yes. Here really this x is to the power of 0, which would be 1. So if you add 1 to 0, you get x to the first power. Yes, definitely. And divide by 1. Okay, so let's look at another example. Let's look at one that... This one's pretty good. So let's look at number 29. This is number 29 on 5.3. I'm integrating x cubed dx divided by 5x to the 4th plus 4 to the 3rd power. So this is what I have. What would be a good pick for you? Anyone? So u equals 5x to the 4th plus 4. So what is du here? I can pick u, but once I've picked u, I have to look at what u is to find du. So if I differentiate u, I get to u. What's the derivative of 5x to the 4th plus 4? 20x cubed times dx. Right? So I have two options here. One option say, okay, I could really use a 20 here. So if I use a 20 there, I have to divide by 20. And I'm fine. So then this is exactly du. Right? So I have 1 over 20, the integral of du divided by u cubed. Or I can solve for dx, and I have dx is du divided by 20x cubed. So I have the integral of 20, or no, there's not a 20 there. I have the integral of x cubed over u cubed, and then dx would be du divided by 20x cubed. So the x cubes cancel, and I'm left with 1 over 20, the integral of du over u cubed.
Why did you put the 1 over 20 in the first one?
Here,
Yes.
because I can manipulate this integral as long as I multiply it by 1. So if I multiply a 20 on top, I have to divide by 20. I multiplied it. 20 divided by 20 is 1. But I grouped this 20 here because this is exactly du. So if I use this 20 here to transform it to du, I have to keep this 1 over 20 out front. So what's the integral of 1 over u cubed? U to the minus 2 over minus 2, right? Because I could write this as u to the minus 3. U to the minus 3 plus 1 is minus 2 plus c. So I have 1 over minus 40, 5x to the 4th plus 4 to the minus 2 plus c. Of course, I could write that as minus 1 over 40 x to the 5x to the 4th plus 4 squared plus c. But generally, I just like to write everything in the numerator with negative powers. It's no big deal. If I was to differentiate it, it would be a lot easier to differentiate this.
You got u to the minus 2 because you brought it up. Okay, what happened to the du?
Once the du is part of the integral, I'm integrating with respect to u. So it means your antiderivative is a function of u. The du goes away as soon as you integrate it. Du is a symbol. If I integrate something, if I differentiate something, I have to differentiate it with respect to something, right? If I have a function of x and I differentiate that function of x, I have to know what I'm differentiating it with respect to. So it's a variable. If I integrate a function, I have to know what I'm integrating the function with respect to. I integrate this function with respect to t. As soon as I integrate it, I drop the integral and the dt sign once I integrate that function.
You just dropped it. You don't plug it back in.
Du is a relationship with respect to dx. You have to always, what am I integrating this with respect to? I'm integrating it with respect to, it's kind of like the limit. You hold the limit out until you actually take the limit and then you drop it. Right? So this is saying you're integrating this function with respect to u. You need the du there. And the reason why here, I could write this as 1 over 20, the integral of u to the minus 3 du. This integral would be u to the minus 2 over 2. Minus 2, thank you. Right? Of course, plus c. So this is, I think you're getting caught up on the notation. Anytime you have an integral, you have to be telling, what am I integrating with respect to? Am I integrating with respect to x? Am I integrating with respect to y? Eventually, this is going to lead to being able to talk about the area underneath the curve. So if I have a function, I might integrate this with respect to x from a to b. Or I could integrate this function with respect to y from c to d. If I integrate it with respect to y, then I have to have a function of y. So if this was, let me give you a specific example here. Let's say y equals x. So if I wanted to find the area underneath the curve from 0 to 1, I would be finding this area. So I would set up the integral from 0 to 1 of x with respect to x. These are my bounds on x. This is eventually where we're going. This tells me that I'm integrating along the x-axis. If I go from 1 to 2 along the y-axis, then I'm integrating a function of y with respect to y from 1 to 2. So I'm finding this area. So the dy corresponds to the y-axis. You can integrate a function of t with respect to t, some variable. Right now we're just trying to formulate how to do this. Eventually we'll get to what it actually means. And it actually means an area underneath the curve from point A to point B. But we haven't gotten to the definite integral yet. So I think this is going to make more sense the deeper we go. We talked about less apparent substitutions.
Now, can you leave this in terms? I mean, eventually we're going to plug something back into u.
Exactly. You don't want to leave it as u. You want to put it back into x, which we did over here, right?
Yeah. Okay.
In terms of x. So let's look at one where we have two options. What is the integral of sine of x times cosine of x? Dx. So it's saying I have a function of x, and that's being integrated about the x-axis. What would be a good choice for you? And you're both right. So here, let's say u is sine of x. What's the derivative of sine? Cosine of x dx. So really I'm integrating u du. Right? If I show how I plug this in, dx is du over cosine of x. So I have the integral of u times cosine of x times du over cosine of x. So the cosines cancel, and I have the integral of u du. What's the integral of u du? U squared over 2 plus c, but u is sine, so then this is sine of x squared over 2 plus c. Right? If I would have made this substitution be cosine, I hate to do this on two pages. Oh, let's see if I can do it. The integral sine of x times cosine of x dx. Let's say u is cosine of x. What's the derivative of cosine? Minus sine of x dx. So if I multiply this by a negative, I also have to divide by a negative, right? Negative 1 over negative 1 is 1. So I have a negative sine x dx. So simplifying this, it's the integral of a minus cosine of x. Sorry, minus cosine, minus u. Minus u du. Which would be minus u squared over 2 plus c, which is minus cosine squared x over 2 plus c. These two equal each other.
So is it easier to use u equals sine of x because then you don't have to deal with negatives?
Yeah, computationally, how much time it takes, they're the same. But yeah, this one you don't have to deal with a negative. This one but these two, if you did this on an exam and half the class did this one and half the class did this one, you're both right. They're both correct. And that's how one way you can get some trig identities, to say that this equals this for some value of c. And it turns out if I set these two equal to each other and I subtract cosine squared to this sign, I have sine squared plus cosine squared, and that's 1. And that's a constant. And that's what this is saying. That sine squared over 2 plus a constant equals minus cosine squared over 2 plus a constant. And this constant can be 0 and this constant can be 1. 1 minus, sine squared equals 1 minus cosine squared. And that's what we have there. Question?
How did you get a negative sign for the first one?
Here? I needed a minus sine x dx to transform that to du. And another way to look at this one, I could say, okay, I have sine of x times cosine of x dx. If u is cosine, then du is minus sine of x dx. So if I solve for dx, I get I get du divided by minus sine of x. Does that make sense? So, if I want this to be u, then I have the integral of u times cosine of x, then dx is du over minus sine of x. Oh, sorry, I switched that. I want cosine to be u, right? So if I integrate this, I have sine of x times u times du over minus sine of x. So the sine of x cancels with the minus sine of x, or sorry, the sine of x cancels with the sine of x. You're left with the integral of minus u du. Which would then be minus cosine squared over 2 plus c, which would be minus cosine squared x over 2 plus c. Sorry, minus u squared over 2 plus c. Then I plug what u is in terms of x, which is cosine of x.
I think maybe to write it out like in steps, you'd understand it better, or people would understand it better. Like step 1, find your u. Step 2, differentiate u. Step 3,
Solve for dx.
Solve for dx, and then step 4, substitute u and dx, and then.
And make sure your integral is only in terms of u.
Yeah.
And in that case, if it's not, look for a less apparent one being there. So yeah, that's a good idea to maybe write out those steps. This will become so second nature that you don't even think about it. Say, okay, this is u du, that's going to be what I need to get it to. So if writing out the steps will help you, yeah, the first thing you need to do is pick a u. And then after you pick the u, you find du. And then you solve for dx from that relationship, like I did here. Then where you have a dx, you plug back in dx in what it is in terms of du. Cancel everything else except for maybe a power of u. And you might cancel everything, and you might have 1. Okay, so they're pretty straightforward. What's the integral of e to the x?
E to the x.
E to the x. So here, this one's pretty straightforward. What are you going to pick u to be? X to the fourth?
Or e to the x.
Well, if you pick e to the x, the derivative of e to the x, so you don't have an e to the x to cancel. What do you have to cancel? You really like to cancel this x to the fourth. Because you know the integral of e to the u. That's e to the u. So what do you want to pick as u?
X to the fifth.
X to the fifth, because that's 5x to the fourth. So then there's a constant to worry about, and the constant, the 9 being there. So if it's going to be 9 over 5, or 5 times 9, or what, you can go through and see that. But then once you get that, you get a constant times e to the u, which is that constant. The integral of a constant times e to the u is that constant times e to the u. Then you back substitute that in.
Can we do this one?
Sure. So let's look at the integral of 9 x to the fourth e to the x to the fifth dx. So if u is x to the fifth, then du is 5x to the fourth dx. Right? Step 1, find u. Step 2, find du. And let's go ahead and solve for dx here. So dx is du divided by 5x to the fourth. So now let's plug in everything that we know in terms of u. So I have the integral of 9 x to the fourth e to the u, right? I'm stuck with that x to the fourth for now. And I picked e to the u because I wanted to replace x to the fifth as u. Now what is dx? Well, dx is du divided by 5x to the fourth. Does everyone follow me there? So now my x to the fourth will cancel, which is exactly what I wanted to happen. So now I'm left with the integral of 9 over 5 e to the u du. What's the integral of 9 over 5 e to the u with respect to u? It's 9 over 5 e to the u. Because the derivative of 9 over 5 e to the u is 9 over 5 e to the u. So now I plug in what this is in terms of x. So I have 9 over 5 e to the x to the fifth plus c. And you can see that this is the exact same thing, pretty straightforward, right? The derivative of this would be e to the x to the fifth times 5x to the fourth, and my 5's are going to cancel. I'm going to be left with the 9 out front. It's exactly what I get here, right? Go ahead and write this up. The derivative with respect to x of 9 over 5 e to the x to the fifth equals 9 over 5 e to the x to the fifth times 5x to the fourth, which is back to my original expression. You see how that might be kind of difficult coming up with that out of thin air, especially with constants. The composition here, e, derivative of the outside evaluated the inside times the derivative of the inside, and that's what we have here. Make sense?
So is there any other way you can do this without the x to the fifth? Like
No.
choosing another.
If this was x to the fifth, we couldn't do it. If this x to the fourth was x to the fifth as well, we couldn't do it because we wouldn't have anything. We'd be left with an x, right? If I pick u to be x to the fifth, I have to have an x to the fourth to cancel.
Just,
Right? Go ahead.
just real quick, I don't understand why it is we treat e to the u differently here instead of, because I understand that the derivative of e to the u is e to the u.
Okay.
But when we integrate other stuff, we have it as like
The power plus 1?
the power plus
Okay.
1 over that.
Yeah,
that plus one.
because I have a variable to a power.
Uh-huh.
Here I have a number to a variable.
Yeah.
Right? So the derivative of e to the x is e to the x. The derivative of x to a power is x to the power minus 1.
Well, we
What am I
try to
doing?
get the
Derivative,
integral
yeah.
there. Yeah. So it'd be x to the r.
Yeah. So
Plus one
if I
over-
have x to the fifth and I differentiate that, that's 5x to the fourth.
Right.
If I have e to the 5x and differentiate that, that's e to the 5x times 5. That does not equal e to the 5x minus 1 times 5x minus 1. That tells me you don't know calculus. This tells me you understand this e to the x. E to the x and ln of x are very important in calculus.
Yeah, and
They're
numbers
inverses
are
yield
not-
each other? Yeah.
Yeah, the number's not very.
Yeah, they're number to a power versus a variable to a power.
So that's 5 e to the 5x.
Yes. The same thing as e to the 5x times 5.
Got it.
Okay, so some of you are getting frustrated, and at this point, you need to just kind of take a minute, take a step back. If you watch, I think there are videos you can go watch, because I don't have the time to necessarily spend on this, but you can go down to probably lecture 5, or lecture 24, sorry. Curve. We are here. You can watch Dr. Delaware's videos on this U substitution, and you can kind of follow through to see how he goes about it. I'm sure he does some examples. See if it will go. So if you're getting frustrated at this, take a breath, maybe watch this and see if it's going to click the next time. Try to do some Wiley videos, or try to do some Wiley problems where you're saying, okay, what am I going to pick here to be my U?
I guess the tough part for me is
It is. That's the very first part. That's the only thing you have control over. Everything else follows from there. So if you don't pick the right U, you're not going to be able to simplify your integration. So what would be U here?
x to the third.
Is it just x to the third?
Negative 9x.
Yeah, minus 9x to the third, because I can deal with constants, that's fine. I want e to the u. So if I pick minus 9x cubed, the derivative of that being a constant to the x squared. And the x squared is going to cancel. You're left with a constant e to the u. And we know the integral of a constant e to the u is that constant times e to the u. and then back substitute. What would we pick here? Well, first off, what kind of form does this look like? It looks like tangent inverse. What's playing the role of u? Just e to the x, right? Because e to the x squared is e to the 2x. So here, what is the derivative of e to the x? E to the x. So this e to the x is going to cancel. You're going to have 1 divided by 1 plus u squared, which is tangent inverse of u. So pretty straightforward there. Here, what are you going to have to be as your u? You could do 12t, and then you're going to have to do another u substitution. Sometimes we'll call u substitution the first one, and then the next one be a double u substitution. But you can all do it in one substitution here. What would you pick as u? Yeah, cosine of 12t, because the derivative of cosine of 12t minus sine of 12t, right, times 12. So this sine of 12t is going to cancel. There might be a constant and a negative to deal with, but then once you get it, you have some constant times u to the 4th. The integral of u to the 4th, u to the 5th over 5, so you have to deal with that constant, and then you're straightforward. Does that make sense? Do you want to take the next few minutes? Yeah. So watching me do it is probably, okay, yeah, I can do that. You need the practice of doing it. And that's why you have Wiley homework, and that's why you have written homework, and that's why I give you quiz before you take the exam. That's why you take an exam before you take the final. So you need the exposure to it. Is there any part of it that, as far as the technique, picking the u, like you said, that's the hardest thing. You can make an error. Let's say you wanted to do u to be sine. So then you have sine times cosine cubed, because you can cancel one of those cosines. So you're stuck with a cosine cubed. You can't get rid of that. So we have cosine. So let's write this up. Cosine to the 4th times 12t times sine of 12t dt.
So you're going to know when you pick your right u whenever you don't have any t's left. Right?
Exactly. So here, u would be just cosine of 12t. The derivative of u would be minus 12 sine of 12t dt, right? So let's go ahead and solve for dt, which would be du over minus 12 sine of 12t. So I have the integral of u to the 4th. I purposely picked u because I'm going to be able to plug it in as u to a power. Then I'm left with sine of 12t, and then dt would be du over minus 12 sine of 12t, which is exactly what I wanted because I wanted that sine of 12t to cancel. So now I'm left with the integral of minus 1 over 12 u to the 4th du, which is minus 1 over 12 u to the 5th over 5 plus c, which would be minus cosine of 12t to the 5th power divided by whatever 12 times 5 is, 60. So rewriting that. You could check yourself by differentiating this. You would get the derivative of the outside evaluated of the inside times the derivative of the inside, which is going to be the exact same thing. Yes. Yeah, off by a negative. All right, so I will finish up kind of what I said we were going to talk about today, but we got sidetracked. Tomorrow we will do a little bit on 5.4, but go into 5.5, and then I'll give you your quiz on 4.8 and 5.2. 4.8 and 5.2.